In last lecture, we saw how we can solve the recurrence relation to get the time complexity of an algorithm using the substitution method. There is another way to solve the recurrence relation that help us solve the relation fairly quickly, and it is using the master's theorem. If the recurrence relation you find out is of form Tn equals to Atn divided by b plus Fn, where the value of a is greater than or equal to 1 and the value of b is greater than 1, then you can apply the master's theorem to solve that recurrence relation. Master's theorem is a kind of shortcut of solving the recurrence relation. So using this theorem, the solution is calculated as Tn equals to n raised to power log a base b multiplied by un. Here the value of a and b will be known to us. The only concern is how we're gonna know the value of un. So the value of un is dependent on hn. We do have a table between un and hn. From there, we get the value of un. But before writing that table, let's see how to calculate the value of hn. The formula is hn equals to fn divided by n raised to power log a base b. Here fn will be given, a and b will also be given. Now let's see the table to get the value of un from the hn. So if the value of hn we get is n raised to power r, where the value of r is greater than 0, then the value of un is or square. And if the r is negative, then un is o1, constant time. And if the value of hn is log n raised to power I, where I is greater than or equal to 0, then the value of un is O log base 2n I plus 1 divided by I plus 1, where I is any number that we are getting as a power to the log n here in the hn. Now let's try this theorem. Let's take an example. Let's say the recurrence relation that we're given is Tn equals to 16Tn divided by 2 plus n squared. After applying the master's theorem, the value of Tn is n raised to power log 16 base 2 plus un. Now here we have to calculate the value of un, which we can get by first getting the value of hn. So if we calculate the value of hn, we will have n squared divided by n raised to power log 16 base 2. So if we solve this, log 16 base 2 is 4, so it becomes n raised to power 4, and n raised to power 2 divided by n raised to power 4 is 1 divided by n squared, which is indeed n raised to power minus 2. Now it is time to get the value of un according to this hn from the table. So here we are getting n raised to power minus 2. So we are getting minus 2, which is the value of r, and it is negative, so value of un is o1. So here we're going to put this constant time o1 in the equation for tn. So here we put the value of un, which is o1, and this is the final value. Let's solve this. So n raised to power log 16 base 2 is n raised to power 4. So the final solution is O n raised to power 4. So this is how we can find out the time complexity using master's theorem. If you can remember these formulas and table, you can go with this easy way of directly applying the master's theorem. Else use the substitution method. And also don't forget to check on the form of the recurrence relation. It must be Tn equals to A T n divided by b plus fn, where a must be greater than or equal to 1 and b must be greater than 1. If you have a relation something like this, Tn equals to 4 Tn minus 3 plus n squared, see here the value of a is 4, which indeed satisfy the constraint, but the value of b here is 1 which does not satisfy the constraint because the value of b must be greater than 1. So this relation can be solved using Master's theorem. You have to go with the substitution method here. So hope this section was helpful in making you understand what are recurrence relations, why they are so important to understand, and how to solve them and where we're gonna need them. So this was all for this topic.